are not clear where to post it, but anyway, I'll make some arrangement to post this screen recordings. Okay, you won't see my face, but you will see the screen and the voice. Anyway, the face is distracting, so better. So let me walk you through the course content. Before that, okay. So this is the module that we are going to okay, so this is structural analysis 1, and I'm Gobi and I'm your resource person for this module. So the next part is understanding about the module content. So let me show you this. So structural analysis 1 is a 4-credit module, which means that in a week we'll have about 3 hours of lectures and tutorials, something like that. Okay, that is equivalent to 4 credits. And there are some prerequisites that you have successfully completed the engineering mechanics and engineering materials and the mathematics 1. So lectures we have 2 hours a week, and then 1 hour tutorials on each week. So we have the lectures on Wednesday. Today is Wednesday. So Wednesday 1:30 to 3:30, and another lecture for about 1 hour on Thursday. That is 3:30 to 4:30. And a tutorial on Friday, that is 2:30 to 3:30. So as you have seen in the previous occasions in your first year, there is an aim for each of these modules. So this module aims to provide further learning on some of the materials discussed under C1011 Engineering Mechanics. We will be focusing on analysis of statically determinate beams and statically indeterminate beams. We will come to a state, we'll see in the future how do you define statical determinacy if you don't know it. So there are several methods we use to analyze the beam. I know that many of you would have heard from others that there are several computer programs available to analyze a structure. However, it is fundamentally important for us to know how to analyze a simple structure using manual calculations. That is, you derive a set of equations and then you solve the problem and find the forces, reactions, stresses. It is very important because although we might be using these softwares when you graduate and go as an engineer, but it is necessary to understand the basic. So understanding the basic comes from these manual calculations that we do. Okay? So there are 4 learning outcomes in this module. That this is the learning outcome means, we expect you to achieve these at the end of the semester. When you complete this course, this module, we expect you to achieve this. That is, you should be able to apply key concepts of equilibrium, compatibility and constitutive relations to the analysis of structures. So we'll see what are these terms. Some of these may be familiar to you, some of these may not be familiar to you. We'll see that. Second learning outcome is evaluate deflection of statically determinate and indeterminate beams. So we'll see why this deflection is important. Third, investigate and analyze the key responses of beam structures using appropriate analytical techniques such as moment distribution, slope deflection, moment area theorems, and consistency of deformation. The fourth learning outcome is use structure analysis software to analyze trusses and frame structures and present the results in reports. So we'll also touch about how to use a computer program to analyze the structures or the elements that we manually analyze, so that we can see how comparable they are and what are the advantages of using manual calculation, at the same time what are the benefits of using a computer program. So there are, and this is another important aspect of this, or learning this module outline, that is assessment criteria. How we are going to assess you during this semester for this particular module. So if you look at this particular module, we have a mid exam which contributes 15% of your final mark. And normally the mid exam would cover the learning outcome 1 and 2. Then there will be assignments that covers for 25% of the marks. So assignments means there are quizzes, in-class tests, and computer labs. I will give you the breakdown on this 25% later. Then there will be an end of semester examination that contributes 60%. So if you are consistently studying, consistently updating, consistently attending the computer labs and keeping yourself updated, then you can easily score this 25%. Then there are 2 exams. If you do a decent job, you should be able to score enough mark to score at least a grade B or above. So what is important is that your effort and commitment to achieve this. So as I told you earlier, there are lectures 3 hours a week, and then 1 hour tutorial a week, and then we have labs, that is 2 hours every other week. Okay, and these are contact hours, which means that we are in contact with you, and then there are assessment hours. Say 1 hour country assessment, 1 hour meet exam, and 2 hours end of semester exam. Then there is a time allocated for your reading and independent study. That is, the time we expect you to spend on your own learning. I think you were a batch who probably joined the program during the pandemic. So most of your first year of studies were like online. Because of that, you may have you may have developed some sort of a self-learning attitude or a habit of learning themselves, because you were on your own, and then I think so, you were on your own and learning from different sources. When you come to the campus, here you have other opportunities, like you can learn from your peers. That is, you see your neighbor or your friend and see how he's studying and how he's taking note, and then it's like we tend to copy others. So the peer pressure is something very important for someone to succeed. Okay, so people do everything because of the peer pressure, because you were sent to a particular school because of the peer pressure of your parents, and then you would have bought some gadgets, or you would have bought some clothes. Everything in our life is due to peer pressure. Okay, that is, you compare with others, and you want to be either as good as them, or you want to be better than them. Isn't it correct? What do you think? If you don't have that peer pressure, and if you are doing everything on your own, you must be a monk, because you don't have any pressure from your external factors. So you define your life and you live the life, means that you are purely a monk material. Even we choose a stream. even we choose a stream of studies. Even everything, where you would live, and how, which vehicle you buy, and where you go to exercise, what kind of exercise you do, and the pen, even when you were small, even maybe now, he has that pencil, and you ask him, okay, where did you buy this? And if some of your friends are having food, you go and buy food from that place. That food is better. This is better, and it's all peer pressure. So we compare others, and we try to do better. So what I am asking is that you apply the same here also. You compare with others and try to do better. So when you do that, you of course will do better than others. So that will be driving the entire thing up. So your friend looks at you and try to do better, then you look at him and try to do better, and it goes. So peer pressure and the peer learning is very important. So we learn more from peers than ourselves. Okay, so that's why your reading and independent study time is allocated. So you are supposed to use that. So if you are spending say 42 plus 28, how many hours? So it is 70 hours. We expect you to spend about double that on your own, so that you can have a decent learning and achieve a sufficient outcome of this module. So this is another one important, that is module pass requirements. So to pass this module, you are required to achieve a minimum 45% mark for both continuous assessment and end of semester examination independently. So you have to have minimum 45% on CA, continuous assessment, minimum 45% on the final exam. Then overall you need to have more than 45%. Okay? So when you satisfy these two 45%, of course you will be 45%. And there are some recommended text. I will upload this one so you can see. You can download this book. It's available. You can search and don't come and ask me how to download it. Or there are about 20, maybe 30 copies in the library you can borrow if you want. So I will be referring the first one. Second one also good if you want to do, if you want to do some more problems. Okay. And software, we have a software called Spacecast, which is the one that we use because it's simple analysis. Anyway, this semester I'm planning to introduce you another software, or introduce you some other commercially available softwares that are used in the industry. But we will not go deep into that. You should know, okay, these are there and I can use that. So later things, the content we'll see as we go on. And here, this is, I think they might have introduced to you that there are 12 program outcomes, and then how do we map the program outcomes with the learning outcome. So these are the program outcomes, so you can read. So this mapping shows how low, medium, high means say if you take PO1, overall it's medium. So and if it's PO2, it's low. So PO2 is this program outcome. So here, if you take in the second year, we don't do complex engineering problems. Okay, so that's why it's very low. We don't look at that. But applying the knowledge of mathematics, basic sciences are to a medium level. So that's why this is M. Okay, so this is how you map your learning outcomes with the program outcome. So that basically summarizes this learning outcomes, and the course itself has two components: statically indeterminate structures, statically indeterminate structures. So before we move further into, today I'm going to give you a little introduction, some background. So we are not going to do any serious calculations or anything today. So before we move to the next, further move into the module, okay? So you all did your first year, right? And you decided to do civil engineering, and that's why you are here. So I just wanted to know, okay, why, see, if I tell you some background, say, you can categorize people who you into maybe 3 categories. First one, that you are here because you want to do an engineering degree, and someone might have told you that civil engineering is easier than other engineering fields. That is one option. You can fall in the second category, that you have some interest in civil engineering. You have seen some civil engineering works, and then that's why you are here. Third one, the common category is that your dad has a company that is something related to civil engineering, so he asked you to do civil engineering, or your dad or mom. So that's why you are here. So you may fall into these 3 categories. If you don't fall into these categories, you may fall into others, and you may have your own reason. Okay? So now tell me, okay, I'm going to ask every one of you. Tell me your first name, not the big name, just the first name, and under which category you fall. Let's start from me. You can remember, better to keep the mask. Danusha. Danusha. You fall into the second category, okay? But no need to tell me the truth. What is the name? Fenuli. Fenuli, okay, Fenuli. What's second category, okay. Priya. Huh? Yeah, what category? So first category is that you are here, you want to do an engineering degree, and you found that civil engineering is easier to do, so that you are doing civil engineering. Second category is that you are seeing some buildings and you have some sort of interest in construction related fields, so that's where you are in second. Third one is your dad or mom has a construction or civil related company, and they want you to do a degree, so that's where you are here. Fourth is others, and you tell what others. Right? Second. First category. Good. Askar. First category. Yeah. Malma. Second category. Third category. Joshua. Second category. Kaushi. First category. Rasi. Second name? Rasi. First category. Rasika, first category. Ira. Second. First category. Okay. Damir. Kamu juga. First name? Wait. First. Kamu itu first category. Dhananjay. Huh? Okay. First name. First name? Louder. Your name? Huh? A little bit louder. Okay, and your secretary. Okay, so now you see there are a mix of people. Some are here because they think civil engineering is easier than electronics or electrical or mechanical. Some think someone they have seen something and they want to do civil engineering, and there are some who have the parents have a civil related industry and they want them to study civil engineering. So it's a good mix, and then now it is very important that if I take the first category, okay, the people who thought civil engineering is easier, yeah, it can be easy in some cases, it can be difficult in some cases. There are a mix of both in every discipline. Okay, so as you progress, you will see whether your judgment was correct or not. Second category, a lot of people will, half of you are telling second category. Of course, say if you are interested in a field, I would expect you to do extremely well in the field that you choose. Okay, so you should learn more, you can read more, and then you can develop yourself more. Then the third category, of course, you have a great interest because you have a business, so again you have to make a great effort to be a leader in the industry. So if you want to be a leader in the industry, you need to be highly competent in the knowledge. So if you want to be highly competent in the knowledge, you have to work hard and study hard. Okay? So all of you, we have to work hard so that you can progress without any problem. Now these unit study calendar and the workload expectation will be shared by the year coordinator, and unit study calendar I have already uploaded on the course web, and the enrollment keys you might know, it's module code CE2011. So it's C capital E capital 2011 is the module enrollment key. So if you go to courseweb, you can enroll using that module key. And I would recommend the supplementary revision material. You have studied engineering mechanics already. However, if you are interested in, like just to recap or just to, see some different perspective, you can check this course on Coursera. There are a lot of platforms. I think with this pandemic, there are so many platforms where you can find good quality learning materials. So this Coursera was there even before the pandemic. It is an online platform where you can learn different materials. You can enroll you can just audit it. That means you don't get any certificate or anything, but also you can pay and get a certificate as well. So you can see the course by Wayne Whiteman on Introduction to Engineering Mechanics. So that pretty much a revision of the engineering mechanics that we have learned last semester. Okay, and also you can see the textbook for reading as well. Now let me go to the lectures. I mean, this part of this lecture is a bit of an introduction. Okay, so you can get some sort of a feeling, right? You know, get some sort of a feeling about the engineering and how things have evolved. Okay? Perhaps the science of building evolved as civil engineering. So, at the time these were being constructed, I don't think there was any course or any program or anything called civil engineering. Even there was no one knew what is civil engineering. Everyone wanted to build something. Okay? The same as when you were a kid. If you were playing with sand and you wanted to build a sand castle, everyone, most of you would have done it. I don't know. If you have not done it, try now. You can get some sand delivered to your home and then build some sand castle. So there was an interest to build something. It started with some I think at those early days when I went to Stone Age in the UK, you know, you would have seen, I don't know whether you know Stone Age, I don't know whether I have an image I'll see. So it is some stone columns and something like a beam, you know, it's a circular structure. It's not even a structure, there are some stones are standing in a circle. They believe it is about 16,000 years old. Or not believe, that even archaeological findings show that, you know, that could be about 16,000 years old. And when they try to look at it, you know, because based on where the monument is and where the settlement was, say if you do some archaeological studies, you can find where people were living. You know, you excavate, and if you find grains, you know, barley, rice, or any evidence, so then that means people would have lived there. Otherwise, you won't get rice or barley or any grain under the soil, or some mud, you know, utensils they have used, or clay equipments, or stone equipments like a knife for cutting things. You know, they have made several artifacts, you know, for the day-to-day use. So if you find that there is such thing, then you would you can say, okay, people were living here. And depending on the depth at which you find this material, using carbon study, they can establish, you know, okay, people were living here about 16,000 years ago. So if you find a settlement and if you find a monument nearby, then you have to come up with a theory, say the monument was not there closer to the settlement, but it is a bit away from the settlement. So what they have found, what they are interpreting is, these were built, this Stonehenge was built for the people who have died, and they thought that at some particular day in a year, if you do some offering there, you can get the blessing of those elderly people who have died. I think still that we are continuing the trace of that. After someone die, we do some offering after the 3rd day, 30th day, every year, remembering them. That is a trace of what we were doing thousands of years ago. Because if you look at the human behavior and then if you read some history, still now the death is a mystery. Okay, the death is a mystery. So when one person dies, what happens to that body? There's a body remains, but without soul. So no one can see, when someone dying, what leaves from the body and where does it go? Can any of you seen that? No, right? No one has seen. Even scientists have not seen. So it's a mystery. Still, it's a mystery. So if you think about like 3,000, 4,000 years ago, they have revered those who have died. Say there were some people who are like, who would have protected the village, or who would have been the guardian of the village, or guardian of their clan. So they were worshipped after their death. So in remembrance of that, most of the things were started, they started building something, a monument. Same as that, so that is how the monument started. And then even from the age that people started living in a cave, the caves evolved, and the house that we live these days, it's something that evolved from a cave. Okay, so as your knowledge advances, you tend to be more sophisticated. So your cave becomes, like you build your own cave and then you make it more complex. And then recently I was listening to a news, and then there were some researchers in Israel, and they have studied, during the Stone Age, about say 3,000-4,000 years ago, you didn't have sophisticated cooking. So they were basically, cooking in fire. So it's like currently what we do, barbecuing. It's basically they were barbecuing this. What we are doing in terms of barbecuing is like a Stone Age cooking. Okay, so you just put the meat on the fire and then you eat it. Now you have a little bit of spices and you put the spices and things like that. But they would have had their own spices, we never know. So they were, what they found is, in all the caves, the evidence of cooking was found in the middle of the cave. So these researchers have studied putting fire in different places in the cave and see how the smoke spreads. See, you can't inside a cave when you put a smoke, what will happen is it'll get smoke get filled the cave and you can't stay inside. So if you start cooking, you have to run out of the cave. But so they would have done. See, interestingly what they have found is that they found if you put the fire in the middle of the cave, then you can reduce the smoke intensity in the cave so that people still can stay in the cave, at the same time they can cook as well. So similarly, from the cave we have evolved to a house. We have used different materials. So when these were being constructed, you had only limestone and then granite. Then in the 19th and 20th century, we invented cement and steel, and then we are using cement and steel now. But the construction, the interest to construct something was there because it is revered. I mean, the sites were constructed for some purpose. Now, if you look at this one, pyramids were constructed to bury those kings who have died. Then there are temples were built. So the mystery of death actually caused the people to believe in God. So they started, there is something beyond our control. So, and they started worshipping that. And that's how all the gods are evolved. So these are Greek temples, Egyptian pyramids, and then we have stupas. Say you have the evidence of stupas and in this country, but we don't have many evidence of palaces. Okay, so if you are a king, you would build a stupa. Like if you look at it in Europe, they have built churches and they have built palaces as well. Still you can see palaces of say 15th century palace or 12th century palaces, you can see that. But in the eastern part of the world, you have seen only temples. Why? Why there are only temples remaining from the history? You don't see houses remaining from the history. You don't see palaces remaining from the history. So why only temples? Anyone, any guess? Any guess? Tell something, Any guess? Tell me something, it's just think, why, what I'm saying is correct or not? We have temples and temple-related buildings existing for 2000 years. Why there are no palaces? So this is this human psychology, Why? Any guess? Any guess? How about you? How about you? Well, the reason was, now if you look at in Sri Lanka or if you look at in South India, the kings, all of them belong to one religious group. So if there is a fight between two kings, they will, the main aims, if a king is conquering or if it is coming for a battle with another king, what they will do at the end of the war, they will plunder the wealth, they will loot the country, and they will demolish everything, just to make sure that there was no evidence of this guy exists. But because if you build a religious building, since all belong to same religion, they will not touch the gold. Okay, they will not touch the gold. So that's why they were building temples. Okay? Otherwise, they would have built palaces instead of temples. So if you want to remain in history, you need to, those days you need to build temples. So that's why we have temple built by every king. You know, there are several temples in Polnaru, Kurnagar, everywhere you have temples built by different kings. But you can't see palaces of those kings, because that would have been destroyed or plundered by the person who have conquered. The same thing that, if you go to India, you cannot see so many temples in north of Hyderabad. You can see temples south of Hyderabad, but you can't see any temples north of Hyderabad. The reason is, when the Mughals were conquering India, they didn't give a damn about the Hindu temples. So what they did, they destroyed everything. But fortunately they came up to Hyderabad and they didn't come beyond that. So there are, in every country there are such instances. So that's why in the eastern part you have temples. So these are old temples built by different kings, and they are built by experienced builders. They have gathered knowledge from their families. There was no institution that was teaching how to build a stupa, or there was no institution teaching them how to build using bricks. But they have gained knowledge from the father. Like father transfers the knowledge to son, son may accumulate some more, some little bit more, and then he transfers that to his son, like that on a lineage. On a lineage, it transferred. So few families had the knowledge, and others had other jobs. Okay, someone who were doing fishing, they were doing fishing as a family. someone doing farming, they were doing farming as well. So just like that it was going. So this, then there was a scientific evolution. Okay, so the first time in the history someone tried to interpret the science of building. So that is Galileo Galilei. So Galileo Galilei is generally considered to be the originator of the theory of structures. In his book entitled Two New Sciences, which was published in 1638, Galileo analyzed failure of some simple structures, including cantilever beams. So he tried to scientifically interpret if a building is failing, how it is failing, what happened. So the failure analysis is creating a spark on the mind of someone to see scientifically why this has happened. So even now, if there is a structure is failing, or there is a failure of earth slope, or a failure of a bridge, then they ask a group of engineers to interpret why this has occurred. So then you try to use your scientific knowledge to interpret the failure. Okay, so you can't simply say, okay, this is failed, this is failed. Okay, you're just saying, okay, this is failed. It is like, most of the statement by politicians, right? They say something and there was no reason behind that, and they don't give justification for that, and they don't give a solution for that, because they can't think. So you can't do the same when someone asks you, okay, tell me why there's a crack in this wall, or why there's a leak in the wall. What could be the reason? So then you try to interpret using basic sciences to see what would have happened. So the Galileo was the first person ever to be written a book in which he tried to scientifically interpret failure of some of the structures. But there were some books that were referring how to design, how to construct, etc., etc. But this is the first time the science plays a role. There's a point of start for scientific interpretation. Then Robert Hooke, he developed this famous relationship between the force and deformation, Hooke's law. That happened in between 1635 and 1703. Okay, so this is how the modern science evolved. Then you have the big guy, Isaac Newton came with several theories. So it's a breakthrough, everything in your life now is governed by Newton's law somewhere or other. Everything. The movement of a car, or building a structure, a beam, load, reaction and foundation, everything. So the birth of Newton has revolutionized the science of engineering, or science and engineering. So then Bernoulli came and he developed this virtual work method on analyzing base structures. Then Euler developed this Euler's theory. Still we are using Euler's theory to analyze beams and buckling of columns. Then Coulomb, he developed this analysis of bending of elastic beams. And this book, the Coulomb's book, is considered to be the first textbook on modern theory of strength of materials. So, I think you were doing strength of materials. So you will come across, as part of the strength of mechanics of materials, you will come across this Coulomb's theorems, Euler's theorem, most of the Newton. Newton already is there. In A level, you have learned a lot about Newton's theories. Then Navier published a treatise on elastic behavior of structures. Then Clapeyron formulated 3-moment equation for the analysis of continuous beams. So still some are using this method, and you will be learning this method later sometime. 3-moment equation. Then Maxwell developed this method of consistent deformation and the law of reciprocal deflections. Then this is an important part. Otto Moore developed this conjugate beam method for deflections, and he developed Morse circles. So you'll be seeing a lot about Morse circle as part of the mechanics of materials, and we'll be learning in a couple of weeks' time how to use conjugate beam method to estimate deflection. So now there is a question comes, why deflection? Say, I'll be coming to that later. If you take any structure, there are 2 types of characteristics are there. One is, it is service state characteristics. So a building is serviceable. Other one is ultimate limit state characteristics. So service limit state characteristics, ultimate limit state characteristics. So what is service limit state? So deflection is one of the governing parameter of the service limit state of the building or a structure. Now say you are walking on a bridge, and if the bridge is deforming excessively, okay, even if someone confirms you, okay, this bridge will not collapse, you can walk on this bridge, but still you will be a bit scared to walk because it is deflecting a lot. So someone seeing from the side can see a big deflection on the bridge, so means they will tell you, be careful, because it's a state of comfort. So these service limit state criteria are developed or defined to achieve the state of comfort. So deflection is one. Then crack. So if you are inside a building where you see so many cracks on the wall, on the slab, wide, big cracks, will you be comfortably staying inside this building? You will be worrying, okay, what's happening, will I be safe? You see creak sound and cracks and things like that. Then you don't have the comfort of occupying the space. So crack is one, then deflection is one parameter, then vibration. Okay, so if you are staying in a house, say you go to one of your friend's house along the closer to a railway track, and whenever there is a train passing through, the house shakes. So will you be comfortable to stay inside the house? No. So vibration, cracks and deflection are 3 main service limit state criteria that govern usability of building. So serviceability of building means, or serviceability of a bridge means usability. Can we still use it? So normally a building when you design a building, we expect it to serve the purpose for 50 years. So within that 50 years, it should not demonstrate excessive cracks, it should not demonstrate excessive deflection, it should not have a high vibration feeling due to external factors. External factors are loads. Okay. So if that's so, then the building is serviceable during its service period. So for every building, every structure, every equipment, you have a service period or serviceable life. So conjugate beam method was developed by Otto Moore, which still we can use to analyze statically determinate structures and to estimate the deflection. We will see, in 2 weeks' time. Then Castigliano's theorem is another work that is used to analyze statically indeterminate beams. So you will see that in next semester, how to use Castigliano's theorem. This man developed something, it's phenomenal, that is called moment area method. This is again another method similar to conjugate beam method, which you can use to estimate the slope and deflection in a beam. So you might be thinking, okay, why we are talking so much about beam, okay? If you look at the structure, whether you take it a beam, whether you take it a bridge or a building, see, you can see beams are there. In every house, every building, you see beam and column are the main load transferring mechanism. The slab is resting on the beam, so beams are very crucial. Then columns are much crucial than beams. So if you don't have a strong columns, there's no point of having a strong beams. So you need to have a strong columns. Then foundation is much more important than columns or beams. I have visited and seen some buildings where they have a nice building, but the building is sinking on one side. Okay, so there's a very famous building. You can Google and see later. It's called Millennium Tower in San Francisco. So there are nice videos you can see. You can understand a little bit of engineering behind that. So maybe I'll try to put one small video about the Millennium Tower before we finish. So that building is sinking. Okay, that building is sinking. So it's a newly built building. People paid millions of dollars to buy an apartment. That apartment, the building is sinking. So now everyone wants the money back. No one wants to live in that building. So foundation is very important. So the entire structure is very important. But in one module, we can't study about the entire structure. Then you can do this module and graduate. Okay, but so that's why we do a little bit here, a little bit there. So you gather a lot of knowledge around it. Okay. So then Muller-Breslau, he developed this principles of constructing influence lines. We'll be learning about influence lines in the future. It's a very phenomenal theory. It helps to analyze the building. Then many developed slope deflection method. We'll be learning in this module how to use slope deflection method to determine deflection and slope in a beam. Then this man, Hardy Cross, he developed something called a moment distribution method. How to analyze a simple beam, a statically indeterminate beam. That means they are statically determinate, statically indeterminate. We'll come in detail to that point. Statically determinate means you write three equations or two equations and derive the reactions so that you can solve a beam. But some beams are not solvable. There are too many unknowns and few equations. So if you have three unknowns and three equations, can you solve a problem? Three equations, three unknowns. So three equations can solve how many unknowns? Three quadratic equations can solve three unknowns. So same, if you have four, if you can derive four equations, you can solve four unknowns, but you can't derive four equations because in a three-dimensional thing we have vertical, horizontal, and then you have one moment on a 2D plane. So moment distribution method developed by Hardy Cross. Actually, moment distribution method is still being used in analysis of structures. Even in many design offices, they use moment distribution method to design simple structures, like to design a house or to design a 2 or 3 story building, a school building, a hospital building. These complex softwares are used only in big projects like 20 story, 50 story buildings. So because this moment distribution is capable to analyze a simple structure. So when you look at this analyzing a structure, we have several of these methods available, and prior to the analysis we have to see whether this is statically determinate or indeterminate. If it is determinate, you can simply analyze. If it is indeterminate, you have to choose some of those analysis techniques and then you can analyze the structure. So we are here to learn about analyzing a simple structure, basically a beam. Okay, so how to analyze a beam. So now let me take a few minutes, so I will load you that video you can see. There's no sound.
Opened to residents in 2009, but even before construction was finished, engineers could tell that the building was slowly sinking into the ground and tilting to one side. How do engineers predict how soils will behave under extreme loading conditions? And what do you do when a skyscraper's foundation doesn't perform the way it was designed? Let's find out.
I think the when I connect
heavy. That might seem self-evident, but it can't be overstated.
it taps to the projector sound, I think. Let me.
Times more than an average house. It would be impossible for just the ground surface to bear that much weight, especially in this case where the ground surface is a weak layer of mud and rubble placed during the city's infancy to reclaim.
Can you hear?
The Millennium Tower is the tallest residential building in San Francisco, with 58 stories above the ground and 419 luxury condominium units. The tower opened to residents in 2009, but even before construction was finished, engineers could tell that the building was slowly sinking into the ground and tilting to one side. How do engineers predict how soils will behave under extreme loading conditions? And what do you do when a skyscraper's foundation doesn't perform the way it was designed? Let's find out. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about the Millennium Tower in San Francisco.
Can you hear at the back?
Skyscrapers are heavy. That might seem self-evident, but it can't be overstated in a story like this. An average single-story residential home is designed to apply a pressure to the subsurface of maybe 100 pounds per square foot of building footprint. That's about 5 kilopascals, the pressure at the bottom of a knee-deep pool of water. With its concrete skeleton, the Millennium Tower was designed to impose a load of 11,000 pounds per square foot, or 530 kilopascals to its foundation, about 100 times more than an average house. It would be impossible for just the ground surface to bear that much weight, especially in this case where the ground surface is a weak layer of mud and rubble placed during the city's infancy to reclaim land from the bay. That tremendous pressure is why most tall buildings use deep foundation systems. The Millennium Tower's foundation consists of a 10-foot or 3-meter thick concrete slab supported by 950 concrete friction piles driven into the subsurface to a depth of about 80 feet or 24 meters. Friction piles spread out the load of the building vertically, allowing much more of the underlying soils to be used to support the structure without becoming overwhelmed. The piles also allow the foundation to bear on stronger soils than those at the surface. Driving the piles so deep allowed the building to not sit on the surface layer of artificial fill or even the soft underlying layer of mud, but rather on the dense, sandy soil of the Colma Formation below. This is a fairly common design in San Francisco, with more than a dozen tall buildings in the downtown area utilizing a similar foundation system, including some nearly as large as this one. However, it's not the dense sands causing problems for the Millennium Tower, but what's underneath. Below the Colma Formation is a thick layer of Ice Age mud, locally known as the Old Bay Clay. Thanks to the geologists for that name. When the building was designed, the project geotechnical engineers predicted that it would settle 4 to 6 inches, or 10 to 15 centimeters, over the structure's entire lifetime, mainly from this layer of Old Bay Clay below the bottom of the piles. But even before construction was complete, the building had already settled more than that. I have a video that goes into greater detail about soil settlement that you can check out after this, but let me summarize the high points here. The ground below your feet may seem firm and stable, but when subjected to increased loading, and especially when that loading is extreme, like that of a concrete skyscraper, soil can compress in a process called consolidation. Essentially, the soil is like a sponge filled with water. An increased load will slowly squeeze the water out, allowing the grains to compress into the empty space. Settlement is usually a gradual process because it takes time for the water to find a path out from the soil matrix. But some things can accelerate the process, even if they're not intentional. The Millennium Tower was already designed to put more stress on the underlying Old Bay clay than any other building in the area. However, construction of the tower's basement also required the contractor to pump water out of the subsurface to keep the site dry. This is often done using vertical wells similar to the ones used for drinking water, but usually not as deep. This deliberate and continuous dewatering of foundation soils accelerated the settlement. Then other construction projects nearby began, including the adjacent Transbay Transit Center, which required their own deep excavations and groundwater drawdowns. All these factors added up to a lot more settlement than was initially anticipated by the project's geotechnical engineers. The result was that by 2016, when the public first learned about the issue, the building had already sunk more than 16 inches or 41 centimeters, triple the movement that was anticipated for its entire lifetime. Unfortunately, that settlement wasn't happening evenly. Instead, the northwest corner had sunk a little lower than the rest of the foundation, causing the tower to tilt several inches in that direction. The media had a field day reporting on the Leaning Tower of San Francisco, and accusations started flying about who was to blame and whether the city had covered up details about the building's movement. The developer continued insisting that the building was safe, reiterating that all buildings settle over time and the Millennium Tower was no different. But it definitely was different, at least in magnitude. With so much attention to the building, the city commissioned a panel of experts in 2017 to assess its safety, both for everyday use and in the event of a strong earthquake. By that time, the building had settled another inch and was out of plumb by more than a foot, or 30 centimeters. That's not something you could notice by eye and was probably only discernible to the most perceptive residents, but it's well beyond the 6 inches allowed by the building code. Even so, the panel found that the building was completely safe, and the settlement had not compromised its ability to withstand strong earthquakes. However, they cautioned that the movement hadn't stopped and further tilting may affect the building's safety. At the same time, and despite engineering assessments confirming the building's safety, the condominium prices were plummeting. No one wanted to live in a building that was sinking into the ground with no sign of slowing down. It didn't take long for lawsuits to be filed. By the end of it, just about every person and organization related in any way to the Millennium Tower was involved in at least one lawsuit, including individual residents, the Homeowners Association, the building developer, the Transbay Joint Powers Authority, and many others. In total, there were 9 separate lawsuits involving around 400 individual parties. After many years of complex litigation, a comprehensive settlement of the legal kind was eventually reached through private mediation. The result was that no one took the blame for the building's excessive movement, condo owners would be compensated for the loss of property values, and most importantly, the building would be fixed. During mediation, the retrofits to the building's foundation to slow the sinking and de-tilt the tower were a big point of contention. One early plan was to install hundreds of micropiles, small diameter drilled piles, through the existing foundation down to bedrock. But the estimated cost for the repair was as much as $500 million, more than the original cost of the entire building. Turns out it's a lot easier to drill foundation piles before the building's built than afterwards. The challenges associated with working below the building, like access, vibrations, noise, and lack of space, drove up the price, and the parties couldn't agree to pay such a substantial cost. An unconventional alternative proposed by the developer's engineer ended up resolving the dispute, and as of this writing, is currently under construction. The proposed fix to the Millennium Tower is to install piles along 2 sides of the building's perimeter. That may seem kind of simple, but there's a lot of clever engineering involved to make it work. 52 piles will be drilled along the north and west sides of the tower, all the way down to bedrock. Unlike the original plan, these piles will be installed outside the building below the adjacent sidewalks, saving a significant amount on the construction cost. An extension to the building's existing concrete slab will be installed around each pile, but not rigidly attached to them. Instead, each pile will be sleeved through and extended above the concrete slab so that the building can move independently. The slab will be equipped with steel beams centered above each pile and anchored deep within the concrete. Finally, hydraulic jacks will be installed between each of the 52 piles and beams. Once everything is installed, the contractor will use the hydraulic jacks to lift the building's foundation, transferring about 20% of the load onto the new perimeter piles. That means each one will be carrying around 800,000 pounds or 360,000 kilograms. The goal of the upgrade is to remove weight from the clay soils below the building, transferring it to the stronger bedrock further below and thus slowing down the settlement. The design requires that the holes be over-drilled so that no part of the new piles can come into contact with the old bay clay and put any weight on this weak subsurface layer. The angular space between each pile and the clay will be filled with low-strength material only after the hydraulic jacking operation is complete. Once the building is safely supported, each pile will be enclosed in a concrete vault below the ground, everything will be backfilled, and the sidewalks will be replaced. If all goes according to plan, the settlement on the north and west sides of the building will be completely arrested. With less load on the original foundation, the sinking of the other two sides will gradually slow to a stop, straightening the building back to its original plumbness, but just a couple of feet lower than where it started. Of course, expensive and innovative construction projects rarely do go according to plan, and this one's no different. The city of San Francisco and the design engineers were carefully monitoring the building's movement as construction of the retrofit got started in May 2021. It didn't take long to notice an issue. The vibrations and disturbance of drilling through the old bay clay were making the settlement accelerate. The speed at which the building was tilting and sinking started to increase as the drilling continued. In August 2021, construction was halted to reassess the plan and find a solution to install the foundation retrofit safely. As of this writing, crews are testing some revised drilling procedures that they hope will reduce the disturbance to the clay layer so they can get those piers installed and the building supported as quickly as possible.
At Etihad, we're rewarding workers for offsetting carbon.
Okay, so anyway, you can watch the. I mean, this is the main part, and now this is at and then. So the whole purpose of this video, I think, it's an interesting one. So there are a few things that you can learn from this. Now, from this video that you have seen, they were saying that geotechnical engineers were expecting some settlement to occur prior to the construction. However, the building settled much more than it is anticipated. And the cause for that, why it settled more than anticipated, there are several factors. I just said building constructions, and during the construction of this building, due to dewatering, the building settled. So there are several issues. So as an engineer, what you need to know about is a broader perspective, and not that project, a broader perspective. There was an instance I know that just a case, a similar case study, but not similar, but something relevant. There was this an apartment complex in Colombo 3 called Astoria. So it's in front of Marnam College. There is a apartment complex. So during that construction, there were so many cracks on the adjacent buildings, houses. So some of the houses were completely demolished and rebuilt by the contractor because the cracks were so extensive that the owners claim that they can't live in that house any longer. Partially, some of the reasons that the contractor didn't do a pre-crack survey, and then he started constructing it so that any crack appeared on the building supposed to be the crack from this construction. So you need to have a broader sense of the work before you start. Think about much broader than that particular task. So even here, when you learn structural analysis, not structural analysis, much broader than structural analysis. So what you learn is a little piece of a big pie. So we need to know what is the big pie is first. Second one is if you do a right analysis, if your parameters are correct and if your models are correct, then you can get a good results. So you should not always believe on computer modeling, because computer will simulate the data that you feed into the system. It has no brain. So you should not believe that if you know how to analyze a beam using a particular software, then you know how to analyze the beam. No, it can't be. Sometimes if you provide wrong data, you will get the wrong results and you will believe that results is correct, but once you construct it, it will be a failure. Or sometimes the repair could be more expensive than the original cost. So in this building, the repair is more than the original cost of the building. Who is responsible for the repair cost? You are responsible. The designer, the client, the contractor, all are responsible depending on the liability. So you need to understand basic engineering sense and ability to analyze structure from the basic principles is very important than knowing a lot of softwares. So here you have an opportunity to learn some of the basic analysis requirements. Okay, that is second. The third one is you have to be in terms of transferring or interpreting your knowledge into an actual problem, you need to have a proper and a broader understanding to interpret what you learn. Okay, simplify. Say you know how to analyze a beam, but if you look at this building, if you think, okay, I don't know how to analyze it. So what's the relevance of the beam? Say for example, if you take this, there's a beam here, okay, that beam. So probably at the end of, you know what is beam, right? Okay, the one that horizontally running on top of the column, that is beam. So at the end of this module, you should be able to analyze it. But this beam is very critical because there's a roof, that the roof is transferring the load to the beam. And if you know how to analyze the beam, then you will know how much load is acting on each columns. Okay, because the columns are going to give reactions to the load applied on the beam. So even at the end of this 13 weeks of learning, you might be able to get some idea or basic understanding to analyze these beams. So means that you can analyze at least 30% of the structure using simple hand calculations. Okay, so break down a complex problem to a simple problem and then solve that problem. That is the third most important characteristic of a learning that you can get from this video. So now they have a complex problem, but the engineer gave a more practical solution. That is, you drill some series of piles outside the building and then you connect that existing building to these piles and then you lift it a little bit so that you can level the building and make sure that the building doesn't settle anywhere. So the ability to understand a complex situation and bring a simple solution is a very key element of engineering. When you are here, you do not learn only about how to analyze the structure. So everything, every module that you learn here gives you a sense of logical thinking. Okay? So that is how, when you are an engineer, when you complete an engineering program, you develop. Even now, when you go through the mathematical stream, then you have a sense of a logical thinking. Okay, you develop a logical thinking. So each stream gives you a different way of looking at things. Say, as an engineer, you will look at a problem and you try to understand what could be the cause of the problem and solve the problem. But if you show the same problem to the lawyer, he will think differently. He will try to keep the problem as long as possible and then try to get some benefit out of it. So if you show that same problem to a poet, then he may write some poems about the problem. Okay? So each of us are trained to approach a problem in different manners. So as an engineering student, a person in the mathematical background, you have to develop this skill of approaching a problem more logically and try to find the solution. So that is the main aim. So we are going to learn how to analyze simple structures and how to implement that. Okay, so that is the part of this module. So we stop here now. I'll see you tomorrow again. We will continue this introduction a little bit. From next week onwards, we'll go deep into analysis of simply supported, statically determinate beams and cantilever beams. Okay? So I'll see you tomorrow, and I'll upload these sources to the course web. You can access them. If you have any questions, you can write to my email ID. So I'll see you tomorrow. Thank you.